Okay, let's go ahead and get started here. So thank you everyone for joining today. Welcome to the Consul Virtual Day. This one's going to be a little bit different than what we've done on traditional webinars. So we have 4 different sessions. We've actually pre-recorded them. A couple of them you may have heard over at HashiCorp, and then we're going to have our speakers joining us for a live Q&A between each of the sessions. So throughout the presentations, feel free to drop your questions in the chat. All these sessions have been pre-recorded. We'll be making sure that we upload them on our site. And with that, I'm going to kick it off. So I'm going to have Mishra from our Office of the CTO. He's going to talk a little bit about the Consul Global Scalability Challenge, and then he'll be joining us live here to answer any of your questions. So with that, I'll go ahead and kick things off.
So a bit about myself. So my name is Mishra. I'm the technical advisor to the CTO at HashiCorp. So I work in the Office of the CTO. And the picture that you see of me on the slide there is me rehearsing for opening HashiConf EU in Amsterdam in 2019, which was the last in-person event there. I still remember meeting everyone in the crowd, and also a lot of people in the community. That was really a privilege for me to open the conference for Mitchell and Armand there. Hopefully we can get back to that. For now, we'll try to make the most of this. So yeah, I work in the Office of CTO on strategic initiatives internally with the product and engineering teams, and also externally with our partners like AWS and Microsoft. I'm a computer engineer by training, so went to school for computer engineering. I've done software engineering and operations engineering. I kind of empathize with both developers and operators and understand this empathy towards delivering software. I also work a lot on open source, and I love open source. And here's a few projects that I work on. You might see me on GitHub in the past few years here. All right, let's get into the agenda here. So it's quite a straightforward agenda. So first, we'll talk about some of the history of HashiCorp and benchmarks. And then we'll talk about a scale testing console, in particular with the Consul Global Scale Benchmark that we published in April. And then I'll give you a background on service mesh, in particular the components, especially the control plane that was the focus for this benchmark. And then we'll talk about the benchmark setup, the benchmark tests, and the results, and talk about some of the learnings from it. It's quite straightforward. So yeah, HashiCorp and benchmarks. So in, I think, March 2016, we did our first public benchmark and published the results, which was on Nomad. We did the million container challenge where Nomad scheduled 1 million containers in 5 minutes across 5,000 hosts on GCP. The Nomad team outdid themselves again, so they more recently released a benchmark in December 2020 where they scheduled 2 million containers across, I think, 6,100 hosts across 10 different AWS regions in 22 minutes, which was amazing. So you wanted to bring in the same scale and kind of concepts into a kind of focus and focus them on HashiCorp Console and specifically the service mesh. So why do benchmarks, right? That's one of the big questions that one might ask. So here's a video of Airbus A350, and we talk about the stress testing on the wing here. So essentially, the wings bend, to a really large extent, more than anything that a traditional flight would ever experience. So you'll notice here the wings bend to about 30-35 degrees or so, which is really, really impressive, the amount of force that put on this wing. And there are other aircrafts that might also do this test, and they might go up to maybe 15 degrees or so and then snap. But those aircrafts are safe as well to fly because traditionally a flight might never experience such a stress on the wing. But my question to you is, which aircraft would you like to be on or take flights on? Is it going to be the Airbus or the aircraft that maybe snaps at 15 degrees or so? So the answer is probably the Airbus, and this is where these concepts also could be directly applied to products and software that you use every day. So now I want to take a step back and talk about So a bit about myself. So my name is Mishra. I'm the technical advisor to the CTO at HashiCorp. So I work in the Office of the CTO. And the picture that you see of me on the slide there is me rehearsing for opening HashiConf EU in Amsterdam in 2019, which was the last in-person event there. I still remember meeting everyone in the crowd, and also a lot of people in the community. That was really a privilege for me to open the conference for Mitchell and Armand there. Hopefully we can get back to that. For now, we'll try to make the most of this. So yeah, I work in the Office of CTO on strategic initiatives internally with the product and engineering teams, and also externally with our partners like AWS and Microsoft. I'm a computer engineer by training. So I went to school for computer engineering. I've done software engineering and operations engineering. I kind of empathize with both developers and operators and understand this empathy towards delivering software. I also work a lot on open source, and I love open source. And here's a few projects that I work on. You might see me on GitHub in the past few years here. All right, let's get into the agenda here. So it's quite a straightforward agenda. So first, we'll talk about some of the history of HashiCorp and benchmarks. And then we'll talk about scale testing Consul, in particular with the Consul Global Scale Benchmark that we published in April. And then I'll give you a background on service mesh, in particular the components, especially the control plane that was the focus for this benchmark. And then we'll talk about the benchmark setup, the benchmark tests, and the results, and talk about some of the learnings from it. It's quite straightforward. So yeah, HashiCorp and benchmarks. So in, I think, March 2016, we did our first public benchmark and published the results, which was on Nomad. We did the million container challenge where Nomad scheduled 1 million containers in 5 minutes across 5,000 hosts on GCP. The Nomad team outdid themselves again. So they more recently released a benchmark in December 2020 where they scheduled 2 million containers across, I think, 6,100 hosts across, 10 different AWS regions in 22 minutes, which was amazing. So we wanted to bring in the same scale and kind of concepts into a kind of focus and focus them on HashiCorp Console and specifically the service mesh. So why do benchmarks, right? That's one of the big questions that one might ask. So here's a video of Airbus A350, and we talk about the stress testing on the wing here. So essentially, the wings bend, to a really large extent, more than anything that a traditional flight would ever experience. So you'll notice here the wings bend to about 35 degrees or so, which is really, really impressive, the amount of force that put on this wing. And there are other aircrafts that might also do this test, and they might go up to maybe 15 degrees or so and then snap. But those aircrafts are safe as well to fly because traditionally a flight might never experience such a stress on the wing. But my question to you is, which aircraft would you like to be on or take flights on? Is it going to be the Airbus or the aircraft that maybe snaps at 15 degrees or so? So the answer is probably the Airbus, and this is where these concepts also could be directly applied to products and software that you use every day. So now I want to take a step back and talk about service mesh and talk about some of the components of a service mesh. So let's say you have a service A and you have a service B, and service A wants to talk to service B. They're both in the service mesh. So service A would do a local host call to its local proxy that's running alongside it. This might be a sidecar container. This might be a systemd job on a VM or Nomad allocation and so on. And then the proxy is responsible to finding a healthy service B, and it'll make a mutual TLS call using certificates or so on, and make a mutual TLS connection and connect up to the proxy, the service B proxy. The service B proxy will forward that request up to service B. Right? And essentially, this is how service A will get to service B. It doesn't need to know the IP address of service B. It'll just make a local host call, and everything else is the responsibility of the proxy. But here, the interesting thing is something needs to configure this proxy. So this is where the control plane comes in. So the control plane is responsible for providing service discovery data, maybe certificates and so on, things like in policy rules, traffic shaping rules and so on. And so it is the kind of the component that's responsible for maintaining state in the system, and it's the highly available component of the service mesh. And then you have the data plane, which is just the proxy itself. It's responsible for routing packets from one place to the other after being configured, getting the configuration from the control plane. So this is why we made a focus on the control plane itself, because this is the resilient, kind of the highly available component of the mesh. And this was the main focus with the Consul Global Scale Benchmark, the control plane scalability and understanding how Consul responds to really large scales. All right, let's talk about the benchmark itself. So we did this in, I think, February 2021, and we published the results in April. So we did two important propagation time tests. One was the endpoint propagation time, and the other one's intention propagation time. So for the endpoint propagation time, we had 10,000 hosts on EC2 on AWS. and we scheduled, I think, 178,000 containers. These were applications that were running on the cluster using Nomad. And then we made all of these containers and applications depend on one upstream, common upstream, and we changed that upstream. Now, what I mean by changed is we either deleted it or added it. In this case, I think we deleted the upstream service. So essentially, that triggered a change in all of the 178,000 proxies. And what we saw is 96.6%, which is about 172,000 proxies, updated the configuration within 1 second or so. And this was all done using 5 Consul servers in the cluster. Next test was the intention propagation time. So intentions in Consul are ways to define access permissions of how a service can talk to another service in the mesh. These might also be traffic shaping rules and so on. So for example, whether service A is allowed to talk to service B is something that you can express using an intention, essentially. So what we did here is we created an intention that would affect 9996 nodes. So essentially 9996 agents that were running on these nodes. The 4 nodes that we missed out of the 10,000 were running workloads that might not be related to this intention change. So as soon as we changed the intention, in this case we created an intention, the propagation time from the control plane all the way down to all Consul agents was about 900 milliseconds, which is quite impressive for the extent that we were running it. We had about 5 Consul servers again here, powering the control plane for this experiment. So those are the results, and now we kind of get to a stage where how did we get to those results, right? So let's talk about the benchmark setup. So the benchmark setup actually was quite straightforward. There was no secret sauce that we used, a secret service that we used to optimize and get these results. A lot of the products like Consul and Nomad were running almost default settings with some minor optimizations that I can talk about in the next few slides here. So essentially, we had 5 Consul servers. This made up the control plane for the service mesh, and the EC2 instance that we were using was C5, I think C5D 9x larges or so on. And we had about 36 vCPUs on these boxes with 72 gigs of memory, and they were spread across 3 availability zones. And then we had 3 Nomad servers that made up our scheduler control plane. They were decently sized as well. Then we had 10,000 Nomad clients. Each Nomad client was running a Consul agent inside it, alongside it as a systemd job. And these clients were about C5x largest, so 4 CPUs of vCPUs with 8 gigs of memory, again spread across 3 AZs. And the way we kind of created these clients were to use auto-scaling groups. So we created 2 separate pools with 5,000 nodes each, which made up to the 10,000 node count on the clients here. Then we had 100 load generators. So essentially, these load generators were responsible for just testing whether all of the service configuration in the mesh was correct, and service-to-service communication was okay. So essentially, we routed traffic to a bunch of workloads and tested out the service mesh. And again, I wanted to note here is that the data plane scalability was not the focus for this experiment. So we didn't care about like how fast, how much requests we could put through the system and so on, which of course you could in this really large system. You can go through a really large number of requests. And then all of the setup was in US East 1 in the AWS region. Next, I want to talk about the workload setup for the benchmark. So essentially, we wanted to mimic something in real life and kind of bring that into our benchmark. So essentially, kind of mimic the microservices world that a lot of organizations are in. So we created a 3-tier service architecture. Essentially, we had service A, service B, and service C, the 3 tiers. And service A was dependent on service B, which was dependent on service C. So you'd call out service A, which would call out to service B, which would in turn call out to service C, and you get a combined response. And these applications were basically just returning some text back, so weren't doing much in terms of just workload. So there were about 1,000 unique services per tier, so which makes up to about 3,000 services in the cluster, unique services in the cluster. And each tier had a number of service instances. So we had 10,000 service instances in tier 1. We had 83,000 service instances in tier 2, and we had about 85,000 service instances in tier 3. which makes up to about 178,000 total service instances running in containers in the cluster. Now, this does not account for the sidecar proxies. So if you bring in the Envoy sidecar proxies, this number goes up to 356,000, which is just 178,000 times 2 in total service instances and Envoy sidecar proxies. Now, each and every service instance and the Envoy sidecar proxy was registered with Consul, and there were health checks that were going on just to basically monitor these applications and the proxies. So this is what the service layout looked like. The 3 tiers, you can see tier 1, it goes all the way from A1 to A1000, which is 1,000 each. And then A1 is dependent on, it calls out to B1, and B1 calls out to C1. And the same thing for tier 2 and same thing with tier 3. The unique thing here is that all of these service instances were dependent on one upstream service called Service Hey. Now, I know you'll talk about this name, like how did you come up with this name? I know this is a very unique name, right? Like I can take full responsibility for this naming here. So essentially, if this Service Hey was to change, all of this 178,000 proxies applications will need to update their sidecar proxy configuration. All right, so now let's talk about the benchmark tests and results. So how did we scale up to actually start running all the workload? So we used Terraform, essentially a Terraform apply to start creating all the infrastructure. So we created all the VPC resources, the subnets, all the underlying infrastructure that you need to run this benchmark. Then we created the control plane for the service mesh, which were the Consul servers. Then we created the Nomad servers, which was the scheduler. And then we actually scheduled the workload as well using Terraform. So we applied the workload on Nomad using Terraform as well. But we queued all the workload first. So essentially what we did is, before we created any of those 10,000 nodes, we queued everything up. So in Nomad, you can queue jobs. And then when nodes are available, Nomad automatically schedules workload on them. And we were using a spread scheduling algorithm, so essentially spread the workload across those 10,000 nodes. The reason for queuing these jobs was because we wanted to make sure we optimized for every billing second that we got. We were on a budget, so we couldn't rerun these things multiple times and want to make sure everything comes up okay. So we wanted to optimize, all the kind of the idle time of these instances as well. So and then, so in terms of creating the 10,000 nodes, we used the 2 auto scaling groups with 5,000 nodes each. Those came up almost within minutes. Amazon, when you ask for 5,000 or 10,000 nodes, they just give it to you. So in order to avoid this thundering herd problem, well, all 10,000 nodes or so, like approximately that, would try to join and register services and so on at the same time. What we did is we added a random delay up to 26 minutes on every node. So when a Nomad node would boot up, it would actually choose a number between 0 and 26, and then just wait for that time, and essentially then finally join the cluster and then register themselves. So it kind of gives you a very graceful scale-up action. It did make our scale-up a little bit delayed, but it kind of gave us that, that responsiveness. And doing this actually helped us and kind of instilled confidence in the benchmark. So essentially, we wanted to optimize for success. We were restricted by the budget. We couldn't rerun these things multiple times. So we wanted to make sure we get it right, most of the time here. So here's some of the graphs of what the scaling up looked like. So you had, it took about 51 minutes for all of the 10,000 nodes to come online. This includes the nodes joining and all of the workloads to also be scheduled on those nodes. So both of these things, and everything registered, everything good to go. One interesting thing here is that you see that CPU usage graph. So during the scale up period, you see the CPU usage goes up to about 43% or so. And that's due to all of the service registrations, the node registrations, and also certificate signing requests from the clients to talk to the control plane, and also for the services that were being scheduled that were wanted to be part of the mesh will also get unique certificates to be able to do MTLS in the cluster. So essentially, those certificate signing requests as well were done by the servers. And as soon as you see that you hit the 10,000 nodes and everything is scheduled, the CPU on the control plane on the servers, it just basically it goes down and stays at about 5 to 10% or so on throughout the experiment. So now I want to talk about the results, right? So what were the results when we did the endpoint propagation time test? So essentially what we did is, as I mentioned before, the service Hey, which was the common upstream, we just removed it. We deleted that from Nomad. Essentially that triggered an update. So all of the 178,000 proxies needed to update their configuration at the same time. So what we saw is 96.6% of the total workload, which is about 172,000 proxies, updated their config in under 1 second. On the right, you see the graph of the kind of the latency distribution here. On the left, you see the table that kind of showcases the latency distribution as well. And you can see, P96 is about 564.2 milliseconds or so. One interesting thing to note here in the graphs is this agent coalesce timeout. So essentially in Consul, we had a 200 millisecond timeout that's built into Consul. So what we do is we wait for changes up to 200 milliseconds and then coalesce and batch all of these changes and send one change to Envoy to reload its configuration. And this is basically avoids Envoy to get triggered updates all the time, especially when there's proxy boot ups and so on, and gives you that efficiency in terms of the proxy here. So this timeout's already built in, and of course, if we were to remove this timeout, you might see better results here. I want to talk about the long tail that you saw in the previous slide with the latency. So there's about 3.4% of the proxies that took minutes to update. So in some cases, 5 to 10 minutes, after the endpoint event had happened to update the configuration. And this delay appeared to be a transient network disturbance, and that we saw at this scale. So essentially, you're running 10,000 nodes, and that too in the clouds. In the clouds, essentially, you will see some form of network disturbances. We saw TCP connection drop-offs where the agents would go into a retry back-off. Some agents failed repeatedly to connect to the servers due to transient network timeouts, but due to repeated failures, they were in back-off state and took a minute or more to reconnect. Some agents remained connected to the servers but saw packet loss and TCP retransmits. Next, I want to talk about intention propagation time test. So essentially, intentions in Consul are ways to define access permissions between services. Whether a service is allowed to talk to other services can be defined using an intention. So we created an intention that would affect 9,996 nodes, essentially. And the 4 nodes that are missing here were not running workloads. So essentially, as soon as we created an intention, all the way from the control plane, the propagation time down to the Consul agents was about under 900 milliseconds in this case. On the right, you see the graph for, again, the latency that it took. Again, the x-axis here is the time in milliseconds. On the left, you see the latency distribution table, and you can see P99 is about 815.2 milliseconds. Not only did we run this test on Nomad, but we also ran this on Kubernetes. So we created a 500-node Kubernetes cluster, had about 1990 service instances running on them. They were all kind of dependent on this one common upstream service, very similar to what the example that we saw earlier. So we changed that service. In this case, we created that service, so that registered itself in Consul, and that caused a change that would lead to 1990 service instances updating their sidecar proxies. So that took just under 700 milliseconds for all of these 1990 proxies to update themselves. And you can see some of the graphs here. So on the right, you see the propagation time graph, and on the left, you see the total running pods in the Kubernetes cluster. Next, I want to talk about the benchmark data collection. So we had a lot of data, as you can imagine, with a benchmark of this scale. We used the Datadog platform for all of this. So we collected stats-D data from Consul, Nomad, Envoy proxies, Kubernetes, load generators, logs from Consul, Nomad, Envoy proxies again, and the application itself. We used a fake service application. You can find it on GitHub. We also had APM data for the application, essentially to generate service-to-service traces and to test out whether the service mesh was configured correctly, and also generate latency graphs to test out the data plane here. So Datadog processed about 1.8 billion log events throughout the kind of the period of the experiment, all the way from lower node counts all the way up to the 10,000 node count. All right, with that, I would like to thank our partners. Big thank you to AWS for giving us the credits and the support to run this experiment, to Datadog for giving us the platform to store APM data, logs, and stats-D data, and all the credits to run this and perform this experiment. So big thank you to both our partners here. And if you want to check out a detailed version of this report, so this talk is a 20-minute talk, only highlights a few portions, important portions in the report. So if you want to read it in detail, you can go to HashiCorp.com/CGSB, which is Consul Global Scale Benchmark. So all of the configuration for the benchmark is also open sourced on GitHub. So this includes all of the Terraform configuration and the service specifications for Nomad and Kubernetes. This is all available under the HashiCorp GitHub organization. So you can go to github.com/HashiCorp/console-global-scale-benchmark. If you don't want to read the detailed report, you can definitely check out the HashiCast episode on Consul Global Scale Benchmark that features Paul Banks, who is the principal engineer in Consul, who worked with me on the experiment. This goes into some of the insights and behind the scenes of the experiment and some of the details. So definitely give that a listen. So thank you so much. I really appreciate you all coming to this presentation. A special thank you to the Consul product and engineering teams for building a product that can scale at this extent. Also, a special thank you to the Nomad product and engineering teams for giving us a scheduler to actually run this test at this scale.
All right. So thank you, everyone, for bearing with us on that initial little hiccup that we had. So joining me right now, I do have Mishra on the line. We do have a couple questions come in, but Mishra, we just wanted to hear you introduce the session twice. So that's why we wanted to make sure that we repeated the video. So one thing I did want to let people know, these are being recorded. We will have them posted. Also, I know we aren't doing quite an introduction to Consul. Highly recommend going to HashiCorp.com/resources if you're looking for a little bit more of a high-level overview. But we have a lot of really interesting use cases that we want to make sure we covered in this session. So we're diving in kind of like head first. Mishra, I wanted to ask you, what was kind of some of the biggest learning moments that you had in the running of this experiment? I think we got you muted. There we go. Good. Oh, did we lose him?
Can you hear me now?
Okay. Hey, there we go.
Okay, sweet. Okay, sorry. Sorry about that. So I think to be really honest, the experiment was not smooth at all when we started off working with it. Of course, like a large scale experiment with 10,000 nodes in the cloud with unreliable network and compute, you're bound to see these issues. So we saw a numerous amount of issues, and some of the issues I talk about in the presentation. But I think the biggest learning was that, the resiliency of like the way Consul is architected enables change in sub-second changes across like really large amount of nodes. And this is Consul is not a new product, right? It's been in the industry for many years now. It's production ready for many years. It's hardened on various aspects of like how the underlying system works. I think the biggest lesson was that the cloud is not that reliable as we think. And the second lesson on the Consul side was that we were able to get sub-second, propagation times for intentions, for endpoint propagation, which is what we care about when we talk about service networking and service mesh.
Thanks. This might be a good one because we had a question come in. Obviously, we did a bunch of a large number of changes in a really short period of time. One of the things that the concern is what happens if that fails. So I thought maybe this would be a good opportunity to talk a little bit about streaming and kind of what changes we made in terms of how Consul's actually handling all those changes, and then maybe just some other advice of what Consul does if something doesn't work right.
Yeah, I think the big thing with Consul is that initially the way Consul was architected was much like a kind of a traditional system where the agent, the Consul agents that are on the clients on these nodes would make a long living connection with the servers, and then the servers would send all of the data when there would be any change. More recently, what we changed is with Peter, what you're mentioning about streaming, is essentially what you get is essentially only the change set. So essentially, let's say an endpoint and upstream endpoint for a service changes. the clients that are responsible to know about that event would only get that endpoint change. So that actually helps on the control plane side. So it helps with the CPU performance and so on, gives you pretty decent performance. You're not constantly rebuilding the state and then sending it all down. So this helps with kind of optimizing some of the control plane side of things again. The data plane side of it is actually quite straightforward. Like you get a bunch of data, you make it in a format that the proxy can consume, in this case Envoy, and then you send it over like a very straightforward XDS connection, and the proxy does its thing. So if you think about the control, like people don't often know this, but in a service mesh world, the more complicated and I guess the more performance intensive task, it happens on the control plane side. And this is why the main focus of this experiment was the control plane scalability.
Awesome, thank you. While we're waiting for some other questions to come in, what's next for the scalability challenge? What are we planning on?
Well, we would like to run these challenges more often, but as you know, this is a lot of time. First of all, time-consuming process, but on the other hand, it requires a lot of money. We spend a lot of money, and luckily we have great partners like AWS and Datadog that helped us with this, and we couldn't have done this without them. But if we were to do this every so often, it would definitely cost us money. The next steps are really to figure out a way, at least at engineering and at HashiCorp, to figure out ways to do this more often. At least do annually benchmarks that would benchmark various parts of the project, and especially the new features that are up and coming. So I think that's kind of the next steps. The source code for the product, for the benchmark, and the results are all out there. The source codes can be found via GitHub. If you go to the HashiCorp GitHub organization and look up Consul benchmark, I think you should be able to filter down to the right repository. And then the actual benchmark results, the detailed report. This is only 20 minutes, but if you want to read the whole detailed report and you're really interested, and there was a link in the presentation. It's hashicorp.com/CSGB, I think, which is Consul Global Scalability Challenge. It's like a short form of that.
Well, we did have a question come in on the load balancer side. Curious to get your thoughts. So it looks like customers using essentially an ingress controller to point to their load balancer instead of using the public IP for the load balancer. Do you know if that's something that we could do with Consul as well?
Yeah, so Consul has an ingress system that you can use. I'm assuming they mention a service mesh that they're using. So I'm assuming that you're on Kubernetes, using Kubernetes. So Consul does have an ingress object that you can use, which you can point to. You do have to put if you want that ingress to be publicly accessible, to the internet, then you do need a load balancer to point it. And that's how you kind of expose things in, let's say, a Kubernetes type of environment. You essentially do, the way the networking is set up is that you do need a kube service, which is a load balancer, which points to the ingress. Then you direct all your traffic to that load balancer using, DNS or whatever, it's up to you how you want to kind of redirect traffic to it. And then the ingress should be able to figure out the right service and kind of forward that request. So yeah, you can use that. And yeah, hopefully as we build more and more interesting kind of resources around the kube implementation, we have better ways to do this as well.
Awesome. So I think we're right up at time before we go here, but I had to grill you with a last minute tech question there too. Not just the benchmark data. So Mishra, I want to thank you for your time today. Folks, we're going to be moving on to our next session, which is going to be about Consul on ECS. After this session, Luke Kaisau from the Consul team is going to be joining to answer additional questions for us. So Mishra, thank you for your time today. And yeah, let's go ahead and queue up the next video.
Thanks, everyone. Have a good day.
Hello, everyone, and welcome to my talk on running Consul on ECS. My name is Luke Kaisau, and I'm a senior engineer at HashiCorp, and I work on Consul. So let me share my screen here, and let's get started. So over here, desktop 2. All right. So we'll go over back here to the slides and we'll present. So today what I'm going to be doing is I'm going to be demoing a new tech preview release we have that lets you run Consul on AWS ECS. And if you're not familiar with AWS ECS, it stands for Elastic Container Service, and it's a container orchestrator provided by Amazon. So let's look at our agenda for today. First, what we're going to do is we're going to do a quick intro into ECS for the folks that aren't familiar with it, and we're also going to do an introduction into Consul Service Mesh. Then we're going to talk about the architecture of how we install Consul on ECS. And then we're going to jump into a real life demo. So we're going to install Consul on ECS. Once it's installed, we're going to go through a bunch of different kind of the features of Consul. We can't go through all of them because we don't have enough time, but hopefully we'll cover some of the interesting ones. So yeah, so let's get started on it. So first of all, a little bit of an intro into what ECS is. It's a container orchestrator, which means it takes containers like Docker images, and it lets you run them in the cloud. It's very, very similar to Kubernetes or Nomad. Kind of what the differences are is it's really focused on simplicity, being able to run containers easily. It doesn't have a ton of features that maybe Kubernetes has, but the trade-off there is it's really easy to get started and it's really simple to run things in ECS. If we look over here at this graphic I pulled from their website, the way it works is you have your image. It could be stored in Amazon Container Registry or in Docker Hub or wherever you want. You can submit it to Amazon ECS, and then you can decide where you want it to run. So currently, Consul only supports running in Fargate. Fargate is a ECS deployment, like I think it's called a launch mode, where basically there's no underlying servers that you have access to. So it's kind of like running serverless. So these images are just running out there, and you can't access like the underlying server that they're running on. But they also support running on EC2 VMs, so you could have your own EC2 VMs, and then they can run like the Fargate. They can run the EC2. The ECS daemon, and then that will actually spin up the containers on there, but you have access to them through the VMs. So that's what this AWS regions are. And then there's also a couple other places you can run these containers. Currently, we only support Fargate, but we'll look to support these in the future. So yeah, you're kind of your bog standard container orchestrator. You give it a container, it'll run it for you in the cloud. So if we look at what that looks like for an example application, so imagine we have two services here. We have our client service and we have our server service. So these are two microservice applications. You could imagine maybe an architecture where the user accesses the client service, and that is like kind of the web UI. But then when they click on their profile, it needs to load that from another microservice. And so it calls out to say the profile service, and it makes an API call. So the request path looks like you load the website through the ALB here. It takes you to this task running on the ECS cluster, which is like the front end. But then in order to load the profile, it needs to talk to a backend API service. So it makes an API call over to this service over here, which say is the profile service. And that call is being routed currently through another internal ALB. And so this is kind of a relatively standard organization, the way to run things in ECS. Instead of an ALB, you might use the service map, cloud map functionality, and then use Route 53 for that. But this is pretty simple, the way you run things in ECS. And so if we look at this architecture, there's a couple things that we may want to improve on it. One thing is we may want to have TLS, so encrypted traffic, going through all of these lines here. So you can put a certificate on the ALB here, but then if you want the request from the ALB over to your application to also be encrypted, then you need to like provision a certificate onto your application, which could be a little bit more work. Some folks might not do that. So that's something we might want to improve, is have all these requests encrypted. Another thing we may want to improve is we might want to have the ability to define rules about which applications can talk to other applications. Currently, you can do that through security groups, and so that is available to you. But typically, you might have these kind of these open in your ECS cluster, and so maybe there's something you want to do there around like authorization. In addition, like security groups only let you say like at kind of like the TCP level, which app can talk to which other app, but maybe you want to do more kind of fine-grained rules about how this application can only call this like /profiles endpoint on this application, but it can't call like a different endpoint, for example, like /admin or something like that. So that's something that you might want. So encryption, and then you might also want some ability to define these rules about what app can talk to other app. And then the final thing that you might want is this ability to kind of control traffic. So, say that this application is having some trouble, and you need to kind of make a request to it, and if it times out, you maybe need to make another request to it. It might be nice to be able to control that from this application without requiring a code change to this application. So maybe you want it to retry like 2 times or 3 times if the request fails, to kind of increase the reliability of your application if there's some network issues or whatever. So those are some of the things that we're going to look at that we can kind of accomplish with a service mesh. So the first thing we can do when we want to install a Consul on this ECS cluster is we're going to install the Consul servers. So currently, we support running these as an ECS task, and in the future, we'll support running these in our cloud platform or on EC2 VMs. So the first thing for now is just to deploy it as an ECS task here. So the next thing we're going to want to do is we're going to want to deploy some sidecars into this application. So a sidecar is basically another Docker container that runs in the same ECS task as your application. But this container it's not like the main functionality of the application, but it helps. It's a helper container. So it's kind of like a sidecar on a motorcycle. So yeah, that's what we're going to allow you to do here is we're going to let you add in some sidecar containers. They're going to help with being part of the service mesh. So specifically what we add in is a Consul client. This is going to be used to kind of control things. And then we also add in these Envoy proxies. So Envoy is a proxy. It's similar to like Nginx or HA proxy. It's a really high performance proxy. It's in the CNCF. It's created by Lyft. They donated it to the CNCF, and it's used for a couple of service meshes. And so what we're going to do is we're going to deploy these containers into your tasks. So now this is what your architecture looks like, but your routing is still going through these ALBs. And so now you're ready to actually have the routing go through the service mesh. So what you'll do is you'll redirect your traffic to actually route through the Envoy proxies. And now if we go back to kind of like the things that we maybe wanted out of this previous architecture, let's go through those again. So one thing we wanted encryption for all of our requests when they go across the task boundaries. And here we see that this request now is automatically encrypted. Consul will handle rotating all the certificates for you. Another thing that you maybe want is the ability to set up certain rules about which application can talk to which other applications. Here now, because these requests are going through these proxies, you can imagine putting up a rule on this proxy about who can talk to it. And you can do all this without changing the code for your application. And then we also talked about the ability to set up retries. Maybe this application is having trouble and you want it to retry the requests. Well, now you can configure this proxy here through Consul, and you can tell it, hey, when this request fails, like retry it up to 3 times. And you can make that configuration, and you don't have to redeploy your application. Excuse me. So yeah, you can just like kind of configure the Envoy proxy here through Consul, and we'll show you how to do that. And it can automatically do this retries. You don't have to redeploy anything. So you have this like ability to like live program your traffic, which can be really, really powerful. So that's kind of a whirlwind tour of what we're going to deploy here. So let's get into like the demo here. So the way that we support deploying first the Consul servers, which is our first step here, and also when we adding in these sidecars, is through a Terraform module. So if we go over to the registry here, and we search up Consul ECS, we'll see that we have this module here. So the module has 2 submodules. It has the dev server submodule and the mesh tasks submodule. So the dev server submodule is what we use to deploy the Consul servers. So what we want to do is we want to deploy this task over here, right? It's called a dev server because it's not like a really production ready server. We're gonna be working on that later. So we wanted to make it clear like it's a dev server. And so yeah, the way you do that is you use Terraform. You use this module here, and then you set a bunch of different variables that are required. So let's switch over to my editor here, and we'll go over here to this Consul directory. So here's the Consul server module that we're using. Its source is from the registry there, and we're using version 0.1.1. And then let's go through some of the variables we need. So we need the name of the Consul server. We need which ECS cluster to deploy to. We need the subnet IDs to deploy into. We're also going to be putting a load balancer in front of it so we can see the Consul UI. And so there's a couple of configuration options for that. And then finally, yeah, you have the logs, and we're going to be running this on Fargate. So that's pretty much it. It's pretty simple to run a task on ECS. So let's just go over to our terminal. And if we look here, we're checked out this example repo, which is going to be available later. And so if I cd into the console directory here, I should be able to run terraform apply. And what that's going to do is it's going to I was double checking it was recording. It's going to deploy these things. So I'm just going to pause the recording to make it a little bit faster. All right, so we're back here. And what we've done is we've seen that this has deployed the console servers on ECS, which means that we have a URL here that we should be able to go to. Here we see we're running the console UI. And if we go over to our ECS cluster here and we refresh here, we'll see that we're running one task there, which is the console server. So we've kind of accomplished round one here, which is this server here, but we don't actually have anything running. You can see that there's only one service registered, which is console itself. We don't have any service mesh services running. So the next thing we want to do is we want to deploy our two applications. So let's again look at that submodule. So that would be the mesh task submodule. And so the way we wrote this was we wanted to make it really easy to deploy these sidecar containers without having to know exactly all the configuration needed for them. So we wrote this submodule that makes that really easy. So if we look over back at our terminal here, or sorry, not terminal, but our Terraform. So here we have that configuration here. And so we're using this module here. You can see here we're using the mesh task module, and we have two instances, one for the client application, and then further down, we're going to have one for the server application. So that's going to be, if we go back to our slides here, that's going to be one for here and one for here. So if we look at what we have in that configuration, again, we're referencing the module on the registry in version 0.1.1. Family is basically just the name of the application. So it's going to be called the client application. We have a couple of IAM roles that we need. Here we're specifying the port that it's listing on. So that's the request coming in here. It's going to be coming into port 8080 here, and sorry, 9090. And then again, for the server, we're also going to be specifying a port that it gets routed to on. And then here is kind of where we have some differences. So we're specifying that there's an upstream. So in Console, an upstream is a request that a service that you need to talk to kind of make your request out to the user. So the example we used previously of like the web service, and it needs the profile service in order to formulate its response. Well, that would be an upstream service. So what we want is we want the client service to call the server service. So we need to set the server service as an upstream of the client service. So that's what we do here. We say like the destination is going to be the server application. And then the bind port is where the proxy is going to be listening to. So if we look over here in the diagram, that means that when we switch over to the routing here, that the Envoy proxy is going to be listening on port 1234. And so when this application talks to localhost 1234, it's going to hit the Envoy proxy, and then it's going to route it over here to this application running right here. So if we go back to the config there, we'll see that we've set those two things. And then the other thing here is we specify our containers. So in this application, there's only one container. It's this one here. And then those two containers there, they're going to get automatically added in. So we're running an example application here. It's a fake service, excuse me. And then the only other thing to note here is that we have this list of upstream URLs. So here we can see that we're going to be calling localhost 1234, and we expect that to route over to that other application. I won't go through all the Terraform here. It's going to be available afterwards. So what we should be able to do here is just go over here and run that. So I'm going to go ... and app into apps, and then I'm going to run Terraform, Terraform apply. And again, I'm just going to pause the recording because it takes a minute or two for all this to be provisioned. All right, and we're back. So we had all this Terraform execute, and really what all it was doing under the hood was, if we go back to our diagram here, it was simply spinning up these tasks here for us. So now when we look over here at our cluster, we should see two tasks, or three tasks, with the console server, and then our two application tasks. We have the client and the application, the server, sorry. And then when we go over to our console UI here, we should see these two applications listed. So we have the client app here and the server app here. If we click in here, we should see that in this topology view, we should see that the client application is calling the server application, just like we have in our diagram here with the client application is calling the server application. Yeah, so that's kind of what we wanted to do with everything. And in addition to like the client, we have the client application. We also have this UI for it. So we refresh it again here. So what we see here is the client application is calling out to the server application. and it's showing it through its UI. This is a kind of a nice little thing. It shows all the requests that are happening there. So that's what we wanted to deploy there. And so now what we want to do is we want to look at some of the service mesh features that are available to us. So one thing we want to talk about is we actually already have this encryption. It's already happening under the hood. We don't even know that it's happening because the request between the proxies isn't encrypted, which is okay because it's within a task. But automatically, these requests, when it's going across the wire here, it actually is already fully encrypted. So that's something we've gained here. The other thing we want to talk about is the ability to deny traffic, right? So Consul has this thing called intentions. And what it does is it lets you set authorization rules about which service can call which other service. So for example, what we could do is we could say that the client application, its destination is the server application. And we're going to say something like, don't allow. Deny that. We save it here. And now when we make this request again, it should fail. So we see here that it's getting a response here. It's failing. It's never working. What we can do is we can change that to an allow. Save that here. And now this request, it should work. Okay, it's not working with an HTTP 500, which is a different error. And that's because I've set this up as an example of something that's going to fail in the future. Every other request actually fails right now. But if I refresh here again, it is going to work. So you can see now that we can use intentions to kind of like immediately to control which service can wish to talk to other service. If we look deeper into these intentions, remember how I talked about security groups can kind of let you do this too, but we also have the ability to set up application aware intentions, which we're calling basically like set up certain permissions based on like which paths a certain application is allowed to talk to. So for example, you could say that like it's allowed to talk to / but it's not allowed to talk to say like /admin or something like that. This application only talks to / right now, so there's not any real point to change that. It also lets you control like which HTTP methods are allowed, et cetera, et cetera. Cool. So that's intentions, and that's something we wanted to talk about here. So we'll leave this allow intention in place. And then let's also address another issue that we currently have. So as I mentioned, when you refresh this, every other request here is failing with HTTP 500. So if we go back to our diagram, just what's happening here is this application, it's 50% of the time is failing with a request. So what if we had this application retry those requests so that it would actually work? In order to do that without a service mesh, you'd actually have to make changes to this application. You'd have to write like a for loop for I from 0 to 3 retry this request if it fails. But with a service mesh, you can actually control these things through configuration without deploying this application. So that's the next thing I want to show you. So if we go over to our editor here, we let you actually control Consul through these things called configuration entries, which you can also specify in Terraform. So I'll zoom in a little bit there. So let me just comment this out here, or uncomment it. And let's look at what we have here. So this is a Terraform file, and we're setting up our Consul provider, which lets us make basic configure Consul. And then we're going to configure three resources. So the first resource is for the server application. And what it's doing is it's setting its protocol to HTTP. And this is needed in order to have it know that, oh, it's an HTTP 500. This application uses HTTP. We're going to do the same thing for the client application. We're going to say, hey, that's using a protocol is HTTP. And then the other things to note here is that the kind of that configuration is called a service defaults configuration. And then the name is which service it applies to. So if we look at our Consul UI here, services, we see here we have Consul Vert example client app. And so that's what this is going to be here. That's going to be the server app, and that's going to be the client app. And then the final piece of configuration, which is kind of what the retries is a service router. And so we're going to have the service router apply to the service app. So if we look over here, it's going to apply to this one here that's being called. And what this configuration says is it's going to say, if you get a 500, retry up to 3 times. And what this is going to do is it's going to configure everybody that's calling the server application to be able to retry up to 3 times in order for the request to succeed. So before we apply this, let's just go back here and just like show like 50% of the time it's failing, right? Okay, and the request duration is about 100 micros. Sorry, the duration here is about 3.3 milliseconds. So now let's go back over here. We've uncommented that, so we should be able to go Terraform apply. And I'm just going to pause this recording again, just to make that a little bit faster. Okay, we're back here. So we should see only 3 changes. It's going to be trying to create these console config entries. And so we just type yes to apply those changes. And yeah, it's created all 3 of these entries here. And so now when we go back over here, what we should expect is we shouldn't be seeing any 500s. Well, it could retry 3 times. So on the second retry, it should always succeed. So let's refresh here. And we'll see here that it succeeded, but note that the duration was 40 milliseconds. So maybe that one required 1 retry. Okay, this one succeeded. This one succeeded. This one succeeded. Okay, so you can see here that what we've done is our configuration has said, hey, I want you to retry up to 3 times. And now we have a much more reliable application. But we didn't make any changes to these underlying tasks. You can see that these were started at it's 258 right now, and those were started at 250, right? So you can see that these weren't redeployed or anything. Nothing actually changed to the underlying code. These are still running happily. And so what we've done is we've configured the console. Go over here to this view here. We've configured console here. Console has configured the Envoy proxies here to retry the requests up to 3 times. And without any changes to our application, we have this really excellent functionality. So I think that's really the main things I wanted to show you today. A little bit more about how you can get started. So here, obviously, let's go to the registry.terraform.io and then search for Consul ECS, and you should see these things running here. And then we have an example here, which will actually deploy you an example application very, very similar to what we currently have, where you have the client application and the server application and your 2 proxies. And yeah, we're working on this. We have a couple more cool features coming up in the future. We're going to be able to deploy onto HashiCorp Cloud Platform. So you get HCP Console, we call it HashiCorp Cloud Platform HCP. And so you'll have your server actually, instead of running, we go back to this diagram, instead of the server running here in ECS, it'll be running on the cloud platform, so you won't have to manage it. And yeah, we have a lot of cool features coming up, but that's kind of the intro to service mesh. And there's lots more interesting things you can do around security and traffic control and observability, but we didn't have time to get into that today. So yeah, let me just switch back to present mode here, and I'll show the final slide. So like I mentioned, you can go to the Consul website, docs/ECS. And also all this is going to be available on GitHub, all the Terraform I used. It's just going to be under LKaiso and then Consul Virtual Day-ECS. And yeah, thanks for listening. My name is Luke Kaiso, and you can find me on Twitter at LKaiso. And I'll be here for questions now if anyone has any. So thank you very much. Bye.
All right. Awesome. And we have Luke here, just like he promised that he would be. So this is great. Awesome presentation. So if you have any questions, feel free to drop them into the Q&A box. We'll go ahead and answer them here. While we're waiting for those to come in, Luke, you kind of hinted at some of the cool stuff that we're looking to do. You want to share a little bit about kind of what's on the roadmap for Consul and ECS?
Yeah. As I mentioned, and let me know if you can't hear me. As I mentioned, what we're looking at is being able to run the Consul servers in a much more kind of production ready environment, which is going to focus on being able to run them in the HashiCorp Cloud Platform, which kind of takes away from a lot of the burden of operationalizing these things. And then yeah, we're also just really kind of open to folks trying it out and saying hey, I want to do it like this, I want this feature or whatever. So the roadmap, other than the HashiCorp Cloud Platform support, is kind of open. So yeah, interested in folks trying it out.
Cool. We did have a question come in related to Envoy. So maybe you want to talk a little bit about so the question is, are retry joins or retries unique to Envoy, or can we do that with the built-in Consul proxy that we built?
Yeah, thanks, Lauren. That's a good question. So in general, the Consul built-in proxy is really only for super kind of try it out use cases. But most of the really exciting service mesh features are only supported in Envoy. So including retries, but not just retries. There's a bunch of other things that aren't supported in the built-in proxy. So yeah, we recommend folks use the Envoy proxy. And if there's some reason why that is like the main difference between the built-in proxy and Envoy proxy is you need to have like the Envoy binary like on your system. So if you're having trouble getting that working, then let us know. But yeah, we recommend using Envoy proxy for anything other than like your very first kind of try it out use case.
Thanks, Luke. So we had a question come in about Fargate. Is this something that users could avoid, or would that require additional changes? So I guess basically you have to run this on.
So right now it's only supported in Fargate, but we do have on our roadmap to be able to support ECS EC2 as well, and it's not that much harder to get that support there. So if the person's asking that, like, do I have to use Fargate? The answer is no. We're going to support ECS EC2. Yeah.
I think that was the question. Thanks. This might be a good one. Maybe talk a little bit about I know there's always some questions about like how Consul Service Mesh compares to like Anthos. Maybe just talk a little bit about the differences there and kind of what we offer versus what Google seems to be trying to do with that solution.
Sure. Disclaimer, I'm not super familiar with Anthos. But I think like I'd say that the biggest difference is that Consul is kind of platform agnostic. Versus Anthos is very much like you have to have everything in Google Container Engine or Google Cloud Platform. So I'd say that's the bigger difference is that we support like many different platforms. Like I don't think you could actually no, I do think Anthos supports managing things in other platforms, but so I could be wrong about that. But I think in the end, like you're going to be like your control plane is going to be in Google Cloud Platform, which might be a bit weird if you're running something in like I don't know if it supports running in ECS, but for example, like it would be kind of weird to be logging into Google Cloud Platform to manage like your ECS cluster. So off the top of my head, I think that's like the big difference is that it's a unified control plane that works across all these different platforms and doesn't kind of like pigeonhole you and force you to use one forever.
Yeah, I think that's fair. Also, Anthos is obviously a suite of solutions versus, what we're trying to solve for is a very specific type of workflow in terms of like the service mesh challenge, right? Like I think there's some added elements of orchestration and kind of runtime configuration that maybe we're not necessarily looking to dive into with Consul. That is definitely possible.
Yeah. And Anthos is pretty new too, so I think that might be something else to take into account.
Yeah, for sure. So one of the questions that came in was just around I think that you were using the new 1.10 UI. Which versions of Consul does Consul and ECS support? Is it only 1.10 and above, or is it backported to anything else?
Yeah, I was using 1.10 in my demo. It will support multiple versions. It will support 1.9 and 1.10 and further. The actual that was like a beta. So right now the release that you could use out there actually uses 1.9.6, I think. But yeah, it'll support multiple versions of Consul.
Yeah, but it is a slick looking UI, so I don't blame you for using that one. I think 1.10 looks really nice. Cool. Yeah. Let's see. Any other last minute questions coming in here? I just want to remind folks, I did get another question about it. All these sessions are being recorded. We are gonna post them all. Do not worry. We will have all of them broken out into individual sessions and on HashiCorp.com/resources. Cool. All right, Luke, I really appreciate your time today. Thank you for sharing the information also about how to get started with this, folks. I think this is a really cool feature, and there's going to be some great stuff. If you have any other additional questions that come up about ECS, feel free to drop them in, and we can reply to them in the chat. So awesome. Yeah. Thanks, Luke.
All right, thanks.
All right, next up, I have Sridhar Krishnamurthy, who's going to be walking us through some slides first, and then we'll be showing a demo. So Sridhar, I will turn the floor over to you. Let's go ahead and just push this to live. You should be able to go ahead and control the slides now. So the floor is yours.
Got it. Thanks, Peter. Hello, everybody. Good morning and good afternoon for folks joining from the East Coast. What we are going to talk about today is how do we securely deploy and connect service mesh across regions with HCP Console. My name is Sridhar, Product Manager for Consul Cloud, and today joining me in this presentation is Riddhi from our Consul Cloud engineering team. All right, so let's set some context here. If we take a step back and look at the current state of application deployment that are happening and are emerging, first is the transition to public cloud. Clearly, public cloud reduces the friction to deploy compute, so a lot of accelerated migration happening. Second is, if you think about how applications are developed, the microservices comes into play here in terms of giving the teams the ability to concurrently deploy develop their applications and reducing the dependencies between teams. The third part is interesting in that while next-gen applications are deployed using a microservices pattern with serverless, containers, etc., enterprises still have legacy application deployments, such as VMs, even bare metal. So net-net, enterprises end up with a heterogeneous runtime that need connectivity between these services. So with this, let's think about why we need multi-region deployment. There are three broad drivers here. First is reducing the latency. Enterprises want to deploy their applications closer to their end customers and improve the user experience. By deploying the applications closer, the latency is reduced and the end customers are happy, end users are happy. Second is high availability, which is essentially if the services are deployed across multiple regions, it increases the availability, and this will enable enterprises to meet their business continuity or disaster recovery needs. The third is regulations and cost. When we talk about regulations, as we call some vertical markets require specific regulations in terms of data located in a specific region along with the application. When it comes to cost, what we can see is there are some high compute need applications that cannot be replicated across all the regions because of the cost. Now, one way enterprises handle is they deploy their applications in regions that have lower cost, and we know that not all cloud regions are created equal. There are cost differences. And then let those applications act as a shared services or a shared service that other applications and services can reach out. So these are the three broad drivers. Now, what are the challenges? When you have your services deployed across multiple regions, there are a few challenges. First, how does one service discover in real time the location and availability of other services? Now, let's say that it's able to discover. Next comes the traffic management problem, which is essentially how do these services dynamically control the routing of other services for progressive deployments, for example, blue, green, or canary, and also how do they observe and troubleshoot the connectivity issues between these applications? Especially if you think of a microservices pattern, you have taken a monolith and decomposed into microservices, and you have replicas running in multiple regions. Now, it's going to be a hard problem to troubleshoot. Third is security. With the expansion of a monolith becoming multiple services again spread across, it is imperative to create a zero trust network, not based on IP, because the IP is ephemeral, but based on service identity. That protects the secure posture of the company or of the applications. As you can imagine, with these challenges, this is where service mesh comes into play. Just for context, service mesh is an underlying infrastructure layer that connects services across different data centers or regions. That's the technology. HashiCorp's Consul is a service mesh, and it started out as a service discovery a long time ago, and we have implemented with Consul Connect, we have implemented the service mesh capability as well. Now, Consul service mesh is available both in open source and in enterprise. It's highly scalable. As Mishra mentioned in the previous sessions, this is a graph of our scalability test, essentially with about 10,000 nodes in which the services are deployed, service instances are deployed. What we see here in this graph is that at less than half a millisecond, about 172,000 instances get the updates. So Consul is highly scalable. And importantly, right from the beginning, Consul is designed for multi-cloud and multi-region connectivity. Let's dig a bit deeper into Consul capabilities. We talked about the challenges, and Consul exactly solves those challenges. If you take service discovery, Consul provides real-time health monitoring and health status. As Luke mentioned in the previous session, Consul is a multi-platform service mesh to allow you to securely route and monitor the service-to-service communication, not only across regions, but across multiple runtimes. The last but important part is that Consul also reduces the operational burden of manually managing the networking tasks with the level of automation that enables you to, for example, let me take an example. If you have a load balancer in the ingress connecting to your Kubernetes or VM clusters, Consul has the ability to dynamically update the pool members of those third-party load balancer appliances and or firewall appliances. Thereby, it reduces the operational overhead. Now, we touched upon the Consul capabilities, but if we take a self-managed Consul, an enterprise must still have to install and manage the lifecycle of the Consul. Can it be done better? The answer is yes. This is where HCP Console comes in. HCP is HashiCorp cloud platform in which Consul runs as a service, and it's a managed service mesh. We launched HCP Console in AWS in February 2021. Broadly speaking, there are three value positions for HCP Console. One is it's a managed service with enterprise features and SLA, and it allows the heterogeneous deployment of your workloads. Workloads can be in EC2, EKS, and ECS. Second is it's designed to be the platform is designed to be secure by default, and the Consul clusters are highly available. It's just one click. If you take the UI, and then the 3-node clusters for production deployments are available to you. Last, when it comes to cloud, it's important to have a flexible consumption model. HCP Console is available both in on-demand as well as in annual subscription. So with the context on HCP Console, let's talk about what we are announcing here. So with the HCP Console Federation feature that we are going to GA in July, the multi-region connectivity can be made simple. First, what does simple mean here? When it comes to HCP Federation, the users, when they create multiple clusters, they enable federation. HCP automatically creates connectivity between the different Consul clusters that are part of federation and establishes the security rules such that the backend work of connecting across these different clusters are automatically taken care of by HCP. The figure on the right, what I'm showing you here is just for illustration purposes. Essentially, there are two regions here. I'm just picking two regions for the purposes of federation. While we can have globally across different regions in AWS, you can set up the federation. Here, the cross-DC, RPC, and WAN gossip, all those connectivity and the protocol, all those are automatically set up by HCP for you. Now, just in this particular context, I wanted to also touch upon the fact that the Consul clusters can be connected to your workloads by two methods. One is by peering from our HCP Console into your workload VPCs, or using transit gateways, where we can connect to your enterprise managed transit gateways, and behind the scenes, behind the transit gateway, you can have multiple of your VPCs reach out, and thereby you can have a multi-point connectivity. Without further ado, I am going to hand it off to Riddhi to show you a demo.
Thanks, Sridhar. We'll go ahead and queue that up.
This is Riddhi. I'll be doing a demo today to show how multi-region service networking can be simplified using HCP Console and Console Service Mesh. The diagram you see here is a visual representation of what we'll be walking through in the demo today. For the demo, I'll be using a sample application called HashiCups. It is a simple app that lets me order a cup of coffee. My use case is that I wish to deploy microservices of this application in Kubernetes clusters spread across different regions, and at the same time secure and control traffic flow between these services. The different services of this app include a front end, a public API, and some backend components like a product API and PostgreSQL database. So now I'll walk through how we can solve for this use case. So stay tuned until we can order ourselves a cup of good coffee. For the demo, I already have the Kubernetes clusters created in the different VPCs. Next, we'll create the HashiCorp Cloud Platform Managed Resources that you see in the top half of the diagram. This includes 3 HCP Console clusters, all part of a single federation setup, in the regions you want your services running in. The 3 regions I'm using for the purpose of the demo are US West, EU West, and EU Central. To do this setup, I use Terraform. We'll be sharing the relevant repo for the demo at the end of the presentation, but the main thing worth calling out in the Terraform setup is how we create this multi-region federation. We create the 3 HashiCorp virtual networks in the relevant regions, and since we use AWS as our cloud provider, these are nothing but AWS VPCs. The peering or connectivity between these VPCs is also managed and created by HCP, and this is important for federation to work. On the right, you can see how with just a few lines, we can set up a multi-region HCP Console federation, and to add a cluster to this federation, we just need to specify a link to the primary cluster, and the rest of the setup is the same as the standalone cluster setup. I went ahead and applied this Terraform config. So let's look at the HCP UI to see the resources that were created. There are the 3 HVNs created in the 3 regions and the 3 console clusters created within those HVNs. Ignore the limit warning on the top. It's only because I'm using a development account. One thing to note is once the federation feature is released, you'll also be able to view federation related information on this UI. We can click into any cluster to view further details about it, like the ID, the tier, the size, the assigned HVN, snapshots if any, and lastly, all the details required to access this cluster. Since I've created a public cluster, I can use a public URL from the UI and access the console UI directly. And to log into it, I can generate an admin token from the HCP UI as well. Once logged in, I could see that the federation was successful by looking at the drop-down list where all the clusters or console data centers are listed, and we can easily even navigate between them. If you see here, right now the only node listed here is the leader node created by HCP. For the demo, I've used a development cluster, but ideally for production, you want to use a 3-node server setup. Now, in order to connect my clients to these managed servers, I can download a client config file from the HCP UI as well, and this helps me configure the clients on the EKS clusters to join the managed HCP servers. I go ahead and do that and install Console on each EKS cluster using Helm. And since I'm using a 2-node EKS cluster, you can see if we go back to the console UI that there should now be 2 additional nodes or console clients listed as members for each data center. I also configured my clients to have a mesh gateway, and what this helps with is routing encrypted service mesh traffic between the data centers. So with all the infrastructure in place now, I can finally go ahead and deploy my application. I went ahead and deployed all the microservices in the different Kubernetes clusters, and this also automatically registers these services on Consul. So if we go back to the Consul UI now, we can see the product API and the Postgres service in EU Central. We can see the public API registered in EU West and the front end registered in US West. Also notice how each service has a sidecar proxy that's registered along with the service. This helps with all the inbound and outbound communications between the services, and also make sure the TLS connections between the services are always verified and encrypted. Now let me try to connect to the front end. In order to do this, I use another service mesh component called the ingress gateway, which provides me an entry point into the service mesh. I can use the URL of the ingress gateway along with the port on which my front end is listening on and try to load my application. You can see I get an RBAC access denied error. This is because by default, Consul restricts all traffic between services unless explicitly enabled using service intentions. You can see the same warning show up on the Consul UI as well. And under the intentions tab, you can see right now we have no intentions or permissions defined. So for my use case, I want the traffic to be forwarded from the ingress gateway onto the front end, onto the public API, onto the product API, and finally to the PostgreSQL database. So I go ahead and configure my service permissions accordingly to control traffic flow. So if you go back to the Consul UI, you can now see these permissions listed. And note how we have just specified the service names to define the permissions, although these services are spread across different regions. This is because federation enables multi-region service discovery. Now with all these permissions in place, let me try to load my application again. You can see this time it loaded up successfully. So we're finally at a point where we can order ourselves a cup of good coffee. So summarizing what we did in the demo, we spun up 3 Consul clusters, all part of a single federation setup, using HCP, connected clients to it, and deployed a multi-region service mesh. Federation enabled cross-region service discovery. The sidecar proxies helped with routing mutual TLS traffic between services. The ingress gateway provided us or the external traffic a secure entry point into the service mesh, and the mesh gateway helped with cross-DC traffic routing. All these service mesh components enabled multi-region networking in a simplified and secure and controlled manner. That's the end of the demo. Thanks for listening. Over to Sridhar for presentation wrap-up.
Thanks, Sridhi, for the demo. Appreciate it. Just to summarize, first, HCP offers a managed service mesh to securely discover and connect your services across multiple runtimes. Currently, we support EC2, EKS, and ECS. We talked about HCP Console Federation that's coming in July 2021. If you're interested in the beta program, please sign up for an HCP account. We have the links here, and then email us at hcpbetaprogram@HashiCorp, and we'll enable you the beta access. As Riddhi mentioned, I have added the repository for the demo, and if you're interested in getting started, there's a link to Getting Started Guide, as well as the link to features and pricing of HCP Console. Thank you. Over to you, Peter.
Thanks, Sridhar. Thanks, Riddhi. We have both of you on here, and we had a great question to kind of tee things up here. Obviously HCP Console is on AWS. Could you, Sridhar, maybe talk a little bit about the differences between HCP and HCS, HashiCorp Console Service on Azure, for those who aren't familiar, and then talk a little bit about Federation on HCS.
Yeah, sure. That's a good one. HCS we have Consul on HCS. Essentially, HCS is a native integration with the Azure Marketplace. Whereas in HCP, what we have is the Consul service runs on the HCP platform. So if you think about billing and user identity, etc., when it comes to HCP, the platform takes care of it. Whereas in Azure, it's a direct integration with Azure. You use your managed app ID to sign up for accessing HCS. There was another question, I think, Peter. What was the second part?
So the question is, because we were talking about federation and HCP, how does federation apply to HCS?
Got it. Yeah. So federation is already available in HCS, and with HCP we are introducing right now.
Yeah, and for the user that asked this question, I'm going to drop a link to our blog where we announced that HCS Federation is available. So if you'd like to start connecting multiple Azure regions together, you can do that now. Cool. Let me go ahead and send that, and let's see what other questions we have coming in here. Give me one moment too. So yeah. So one of the questions that we had, and Rita, you kind of touched on this a little bit in your demo, but maybe you talk a little bit more about why would I want to use federation? I know in your demo you set it up to where I had different services running in different HVNs, but is that normally what I would do, or are there other use cases that I'd want to use federation for?
Yeah, I think the main use case for federation is driven out of the need for having a multi-region service mesh. So if you have in console land, they're called data centers. So if you have multiple data centers, wherein these data centers are in different regions, I think that use case is where the federation solution comes in, as Sridhar went over in the demo. And how this ties into HCP is HVN. HVN is nothing but depending on the cloud provider you use, the underlying cloud provider you use. For example, we used AWS. So it's nothing but a dedicated VPC in the desired region. So you get that network isolation. And the suggestion to use multiple HVNs is because you have multiple regions and you technically are connecting, creating a VPC in each region, and hence an HVN on each region. So it is an abstraction on the HashiCorp cloud platform side. But under the hood, depending on the cloud provider, it gives you that network isolation provided by whatever the provider does, for example, VPC.
Yeah, and also just, I'd like to even tack onto that. Oh, Sridhar, I think you were going to add something.
Yes, that's a good point, Riddhi. In addition to what Riddhi said, the other use case for federation that, depending on the scale and size of the enterprise, is that if you want to dedicate a set of console compute to one line of business, but yet you want to discover services from the other lines of business, one way to do it is that you create separate console clusters based on the lines of business and then federate between the two. Even it may be in the same region or across regions, but that's another from the purposes of resource isolation, where you could create separate console clusters and federate among them. It's made easy now. Now you no longer have to worry about how do I connect to the other service, because all the HCP platform automatically takes care of it. It takes care of it. You have to just express the intent, and the platform will take care of the underlying plumbing.
Yeah, this actually leads in really well into another question that we just got. So what happens if I have the same service deployed in multiple regions? Does the traffic prioritize the region that it's within, or can I set up like a traffic router or a failover to a different region? Open it up to either of you. Sorry, I should have directed that to somebody.
I think, yeah. One of the console engineers might be able to answer this, but I'm less aware if there is prioritization of that sort. But if Kyle is around, or Nitya, or someone who's more console federation experts, if they could take it, or we could answer this async.
Yeah, I do know that one of the things we can do with this is if you do set up traffic resolvers, that we can set up the versions that you want to be able to route to, including the weights and splitters that you want to be able to route to as well. So depending on if you were going to use federation, for instance, for redundancy, for this user, you may want to set it up to have a failover policy that if the service is unreachable in your local data center that it knows to route to a different one. And it looks like Kyle's going to go ahead and fill out even more of the answer than I can there. So appreciate that. Cool. So let's see here. What other questions do we have? Yeah, so Sridhar, you kind of mentioned this, but let's maybe cover again, like what's the best way to try out Federation?
Signing up for beta at the moment. Once it's generally available, you can directly go to the portal and pick it up, select the option and move on. But in the interim, as the slide shows, if you are able to sign up and get an account in HCP Console and connect us via the email HCP beta program at HashiCorp, we would be delighted to include you in the beta.
Absolutely. Great. Okay, cool. Thank you both very much. Oh, yeah.
Peter, can I interrupt? Sorry. So there was one question in addition to the question Christoph had asked, where if there's a preference towards AWS when choosing between HCP and HCS. I don't know if we covered that bit, but my take on that question would be it would be driven by where you want your clients to be in, which cloud provider you want your clients. So the interface to it would define which cloud provider is your preference. Sridhar, if you have something to add to that question.
Yeah, sure. So essentially, since the discussion primarily in this particular case, the topic is kind of centered towards AWS. So here you hear a lot about Consul in AWS. We've had other webinars where we have talked about HCS in Azure, and we are more than happy to share with you some documentation around the offering that we have on HCS in Azure.
Yeah, absolutely. No preference one way or the other. Just we were introducing Federation for HCP, which is running currently in AWS only. Federation is currently available on HCS, so actually it's a little bit ahead. So some HCS users might be already federating between multiple clusters, which would be great. So awesome. Cool. So we're going to go hit our final section here. Reedy, Sridhar, thank you so much for hopping on here and giving some answers to these questions. We'll go ahead and queue up our last video. We're going to talk about transparent proxy, which is new as of 1.10, and that's going to include Nitya and Kyle. So there we go. Go ahead and get this started.
All right. Hey, everyone. So today we're going to talk about a new feature in Consul 1.10, transparent proxy for Consul service mesh. I'm Nitya, and I'm an engineer on the Consul team.
I'm Kyle, also an engineer on the Consul team.
Sweet. So yeah, we'll kick it off with an agenda. So we will focus today on transparent proxy on Kubernetes and what it enables and why it's nice to use. We'll have two demonstrations, a service-to-service use case, which is a bit simpler, and demonstrates just kind of how easy it is to use and the defaults, and a more complex ingress use case, since we're excited to show you what this new feature can enable and give you a better idea of the configuration you can tweak with this feature. And then we'll circle back and recap. So IT proxy? Well, service mesh users want to use the mesh for security and traffic configuration and not have to change their applications or think about what the service mesh is doing under the hood for them. So transparent proxy makes it so that apps don't need to be proxy aware. On Kubernetes, users typically use kubedns to address services within the cluster, and transparent proxy allows you to continue to do that and leverage that tooling, which means you don't need to make changes to your application in order to use the mesh. Also with tproxy, IP tables rules enforce that all inbound and outbound traffic for your pod go through the sidecar proxies. And we'll talk more about this in the example. It also simplifies and makes upstream configuration more dynamic. So let's walk through an example. Before tproxy, here's what service-to-service communication looks like. This front-end application has an annotation for its upstream backend, indicating that it wants to reach backend at port 1234. So whenever front end dials the back end, it'll need to use localhost 1234, which will dial its local Envoy proxy. And Envoy is configured to know that 1234 is for the backend application. And in order to have traffic go through the proxies, you do explicitly have to dial localhost 1234. And so it's not enforced kind of through the proxies before this transparent proxy feature. So with transparent proxy, we have something that looks more like this. Service authors can use kubedns to dial their services, and that traffic is always directed through the Envoy proxies. So traffic cannot circumvent the mesh without explicitly declaring that it should. So Consul will configure the proxies to know about any upstreams that they can talk to via service intention config entries. So if you want two applications like front end and back end to talk to each other, you just need to create an intention that allows that, and then dial the kubedns address just like you would without the mesh. So this is one of the demonstrations that we'll walk through today. All right, so we're gonna walk through a demo where we'll deploy Consul. We'll deploy a front-end and back-end application where front-end reaches back-end using the kubedns address. And we'll at first not include the intention, which means that traffic will not reach the back-end. And then we'll add the intention to show how the mesh is dynamically configured to allow that traffic. So first we'll kick off the installation there. And let's take a look at the console values file. So this is the values file that's being used to install Consul here. So we've turned on ACLs, which means that by default, applications will not be allowed to talk to each other, and we'll need to add an intention to allow that explicitly. We've got some servers and clients, and then we've enabled connect inject, which is what allows you to use service mesh and injects the sidecar proxies into your application. We've also enabled transparent proxy, which also already defaults to true, but just to be explicit here, we've turned that on. And we've also enabled the controller, which allows you to use custom resources in Kubernetes for config entries. So that has been deployed. Cool, and so that's up and running. So now we just need to deploy front end and back end. So let's look at the YAML for that first. Okay, so for front end, we've got a service, and a service is used to expose an application in Kubernetes, either to other services via kubedns. So this means that I can reach front end at frontend.default.service.cluster.local, or also from outside of the cluster. And we've also got a service account here for front end, which is required when ACLs are enabled and will allow front end to get an ACL token to use. And we've also got a deployment for front end. And the thing to note here is that front end has just an environment variable here about how it's going to dial its backend, and it can use the backend's kubedns address, which is backend.default.service.cluster.local. So this is exactly what it would do even if this application was just running on Kubernetes without Consul service mesh. And then front end is running on port 9090, so we'll port forward and go take a look on front end whether it's successfully dialing its backend. And lastly, we've just got a service defaults here, which tells Consul that front end is an HTTP application and can leverage Consul's L7 traffic routing, splitting, config entries, and intentions. So we've got a very similar setup for backend. It's got a service account and deployment, and a service defaults. And then we've got the service intentions here that we said we will not include to begin with, and see kind of what happens there. So let's put this up. Right, so those are starting up, and once those are up, we can port forward to front end and take a look. Cool. So port forward. And take a look at the UI. Which might take a little while to come up and show us. Okay, there it is.
Cool.
So yeah, so this is showing us that front end was not able to reach back end at this URL. The response was a 500, and that's because we don't have that intention yet. So let's make sure we add that. Actually, going to kick off the port forward here. So that cool. So that intention has been deployed, and so we should be able to see that traffic actually come through soon. So this might take a little bit too, but we didn't have to make any other changes. So we just have to wait for it to start working. Cool. So yeah, now front end is able to dial back end at this cube DNS address. And we see that the response is a 200. So yeah. Cool. Yeah. So now that we've covered the service to service use case, Kyle is going to cover the ingress use case.
Cool. So just to recap, we just showed you a demo of service-to-service traffic using transparent proxy that highlighted using kubedns as a means to determine where your traffic is going through the mesh. So what I'm going to show is a demo which is a little bit more complicated, but also uses the sidecar to direct traffic throughout the mesh. And that's using an ingress resource. So what we have is a Trafic ingress gateway, and then with it, we would have an ingress resource, which helps define rules for Trafic about how it would actually route traffic throughout the mesh. So the difference between the two demos is that one is using kubedns, and the other, the Trafic ingress, is using pod IPs to direct traffic. So here we have simply rules set up for a host, as well as the backend service which it'll talk to. And so what we'll have is traffic will come into Trafic. Trafic will then figure out which service it needs to talk to and direct traffic directly to the pod IP of that backend service. So I'll go ahead and show you a demo now. All right, so what we'll be demoing is a simple Trafic installation and console installation along with an application that we'll try to reach through the ingress gateway. So in order to do that, we just have to basically deploy those three things. And so I'll just kind of go ahead and do them. So first we'll install Consul. And in doing that, we're just using a very basic console values.yaml file for a Helm installation. This is all fairly standard. I'm just using a dev image of my own. TLS is enabled, ACLs are enabled, and then again, connect inject is enabled. As Nithya mentioned, tproxy is defaulted on, so I just don't have that listed here. So very simple. So I'll just do a helm install Consul. And that'll take 30 seconds or a minute. And so in the meantime, I'll show you what the Trafic values file is. So we take a look at that. This is just a fairly basic Trafic values.yaml file that I grabbed from their website. All of this is fairly basic. The only things that really need to be changed are down here in the RBAC rules. We had to set the service account to be explicitly named the same as our actual service. It just happens to be a requirement within Consul that your service and service account have the same name. That's what we use for authorization. And then again, one other thing is Trafic's going to deploy a deployment. And that deployment we want to actually add a sidecar to, so that when traffic comes into Trafic, it can then go into the mesh and off to the service. So in order to do that, what we do is we connect inject the deployment for Trafic, and then open up a couple extra ports. So Trafic needs to be able to have traffic come into it and have that into the pod and have it hit the Trafic service without hitting the proxy first. If we didn't specify these exclude ports, then all of that traffic would go into Envoy first and not make it to the Trafic service. So we set up the ports that the deployment needs, as well as one additional, which is to set up an exclude of the CIDR range, which covers the Kubernetes API. So Trafic needs to be able to hit the Kube API to grab information about services, grab information about endpoints, objects, and that sort of thing. Since it's managing routing for a service, it needs to be able to grab access to that. So in my case, this just happens to be my Kube service. So if you were to use the same thing, you just point this to your Kube services IP. So back to Consul. Should be up and running. Looks like it's all up and running. All right. And then I'll just go ahead and install Trafic. Just like that. And that only takes a few seconds usually. All right, cool. So it's coming up, and you can see that it has a second container added. So that was actually our sidecar container for mesh traffic. Now I'll let that come up in the background. So now that we've got Consul and Trafic running together, what we'll need to do is then just simply deploy the application. So Trafic has a demo application called Who Am I, which allows you to just curl through the Trafic ingress gateway, hit the Who Am I backend service, and it'll return information about what it is. So in our demo, that's what we're trying to do, is have traffic come into the Trafic gateway, go through the controller, and make it to the through the mesh to the backend. So let's take a look at the deployment for that application. So very similar to what Nithya was talking about earlier, we just have a simple service account and service, which are like the front of this backend. Then the actual deployment itself is very standard. This is a exact copy of their demo. The only difference is I've added a service account because we're using ACLs, and then added an annotation that says, please connect inject this. So that we can just simply apply. Now, Trafic itself is actually managing the routing. So I mentioned earlier that we're not relying on Kube DNS here. So what happens is when it comes into the Trafic controller, it then figures out the pod IP and sends traffic to the pod directly. And so in order for that to work, what we have to do is apply a service default to the deployment in Consul. And so what that looks like is it's a CRD, and we simply say that transparent proxy should allow this pod or this application to be dialed directly. So that means we don't reject traffic that show up directly to the IP address of the pod. So I will just apply that. And we should have our pods coming online. Okay, everything's online. What's next? Oh, we also have to create an ingress resource so that Traefik knows how to actually direct the traffic. So I have an ingress resource that I just copied directly from Traefik's example. And what this is doing is it's setting up a rule for if I ask for a host, who am I, when I reach the ingress gateway, it knows to then go back to the backend service, who am I. So I'll go ahead and also apply that. And now everything should be set up and ready to go. So if I do kubectl get services, I now have an external IP for my gateway, for my ingress, and I should be able to curl that ingress port 80 and pass host header, which we just talked about as the ingress resource. Who am I? So it should now know to go to the who am I deployment, the who am I service, and reach that for this request. So looks like we forgot something. What happened here was that Consul actually rejected the request. And the reason for that is because we have ACLs enabled. And so that says that that tells the system that we're not allowed to pass traffic unless it's been explicitly put in as a rule. So what we can do there is to add an intention. And so for that, it just looks like this. We're creating an intention that says the Traefik service is allowed to reach the destination service, who am I? So if I were to simply just apply this, we would now be able to actually pass all the way through and get a response back. So this worked. That's great. It tells us information about the pod that was actually the pod IP that we actually reached. And yeah. Cool. So that was our demo of the ingress gateway using Traefik. So that was quite a bit of information, lots of YAML files, lots of text to try to consume and hold up here. So I thought I would just kind of give a higher level overview of what we were doing, showing how the resources interact with each other, and kind of hopefully give you a better idea of what was going on here. So again, we deployed a Traefik ingress gateway that takes an ingress resource and it connects a host and a service together so that Traefik knows how to accept that host header and forward it to the backend service. And so Traefik itself, we deployed as being connect injected as well. So that allows us to take traffic that's coming into the gateway, pass it down to the Envoy proxy, and go across the service mesh to a backend service. So we had to do three things for Traefik to actually manage this. One was to simply connect inject it. That creates the sidecar. The second was to set up a few excluded inbound ports. And so again, these are the ports that Traefik is actually using. And what we want to do is make sure that traffic can come into Traefik and not hit the Envoy proxy directly, so that it can then take the traffic and route it as it sees fit. So we set up some excluded inbound ports for that. And then also Traefik needs to reach the Kube API server. And since it's actually managing a service, if you will, it needs to know about what endpoints are part of that service. And in this case, an endpoint is the who am I service itself, which is running connect injected. So that's the Traefik pieces of it. Consul is then responsible in the middle for managing that traffic from Traefik all the way over to who am I in the backend, right? So Consul just simply needs a few things. So one of them is the service so that you can actually connect inject the service for the deployment for who am I. The second is a simple configuration for a service default that says, hey, please allow this service to be dialed directly, not using kubedns, but actually using the pod IP. And if you recall, Trafic actually routes directly to the pod IP, not using kubedns. And then finally, we have a service intention, which is what we're using to tell Consul to actually allow the traffic to go from one Envoy proxy to another Envoy proxy. So I'll spare the rest of the details, but that's essentially what all the resources that we needed to get the demo to work. So that's that. Thank you. Check out Consul Helm and Consul Kates on GitHub. I also have the Trafic demo up on GitHub as well, so you can play with it as you see fit. This is all featured. This is our new big feature in Consul 1.10. So thanks so much. Appreciate it.
Thank you, everyone.
All right. I should have Nitya and Kyle here with me. Let's see. Yeah, there they are. Awesome. Thank you both for that presentation. We'll go ahead and ask a few questions here. I'm a huge fan of Transparent Proxy. I've been playing around with it myself, so thank you all for the work that you did on it. I think it makes using mesh a lot easier. Nitya, you were answering a question here about upstream URIs. I thought maybe you could share kind of that information with why we were using those in your demo app and how they apply to Transparent Proxy, if at all.
Yeah. Can you hear me?
Yeah, you're coming in a little fuzzy. I don't know if it's just me.
Okay, yeah.
Is this a little better?
There we go.
Yeah. So the upstream URI was something that was specific to the front-end app. And you wouldn't usually have to use that. Sorry, I'm getting a bit of an echo here. I'm just gonna, okay. Yeah, so you wouldn't usually have to use that environment variable. That's not something specific to like all pods that you deploy to the Connect service mesh. That was just something that app uses in order to know what backend it's trying to dial. And before tproxy, it would have been useful to set something like the local listener that you need to dial to reach your backend. But with tproxy, since you're just using a service URL, if frontend already knows that it's going to talk to backend, then it could have just used that service URL like in its application logic. It wouldn't have to pass in that upstream URL there.
Awesome, thanks. Kyle, I see you in here answering the question about Trafic, so maybe we'll share that with the group. Does it support Trafic's ingress route custom resource, or does it have to use only the Kubernetes ingress resource?
So I didn't show that in the demo, but you should be able to use it. I have seen it work. So yeah, it does work with the CRDs.
Awesome, thank you. One of the things, and then maybe we can touch a little bit more on this, is I know that you were answering a question on there about service intentions. In the examples that you all gave, ACLs are enabled, which is going to have you can have a default deny in place, but service intentions you don't necessarily need if you're just going to open up traffic to everything, right? Or maybe talk a little bit about just how service intentions relate to tproxy overall.
You want to take that one, Nitya?
Yeah, sure. So service intentions are used when you have an ACL default deny policy. So in Kubernetes, you saw that both me and Kyle in our demos had that managed systems ACLs values set to true. And so that's enabled ACLs, and it's set the ACL default the ACL policy to be default deny. So that means that by default, no two apps can talk to each other. And so you do need to explicitly then set that intention so that in the first case, front end can talk to backend, and in the second case, the ingress router can talk to who am I.
And we're actually
go ahead.
Sorry. In the context of tproxy, we're actually these intentions to set up the IP tables rules, which is defining how everything's being. Sorry for the echo here.
No, you're good, Kyle. Cool. No, I think that's a really good point. Actually, you led me into another question. I think is always good to let people know if I'm interested in using T-Proxy, but maybe I was using Consul Connect before. Is there any considerations that I should have, or is there anything that I should do to make sure that T-Proxy works correctly for me when I'm upgrading to 1.10?
Yeah. So when you're upgrading, you will need a Kubernetes service for every single app. So that's how we tell Consul, oh, okay, this is a service in your service mesh. And you typically deploy Kubernetes apps with Kubernetes services anyway, because that's how you would get a URL to talk to those services. So you will need that. And then if you have existing services that kind of weren't using this T-Proxy mode before, after you upgrade, you will need to restart all of your pods so that they're managed by the new kind of central system that we have for managing pods now.
Thank you. Kyle, I'm going to throw this your way because you showed us the big architecture graph. There's a lot of resources, obviously, that you got to compile for this. Any recommendation for folks that want to be able to build out all the configurations, or any like templating that they could use?
Specific to T-Proxy, there's not a whole lot, right? But in terms of like setting up in my demo, setting up like ingress resources. The three things that we had to change were connect injecting the ingress controller and then setting up the exposed ports. Typically, those are just the container ports of your ingress controller. So it's really just kind of like looking at what your ingress controller needs in terms of like its deployment, and then setting up exclusions for those specific ports.
Awesome. All right, we'll give it a second here to see if we have any last second questions coming in. Again, as a reminder, all these sessions, you got a couple of shout outs. Awesome presentation. I think the demo was fantastic. So make sure I let you know that a couple of people chime in there. These all have been recorded. We are going to make sure we post all the slides and everything, so folks are going to be able to access the demo repos if they want to try this themselves. Let's see. Okay, well, we are at the, let's see. So we did have a question about Traefik middleware. Kyle, I don't know if when playing around with it at all, do you know, is it going to impact any of the configurations you have set up there, or how does it play with some of the Traefik middleware components?
So I didn't get too far into the middleware components, right? That's part of the Traefik CRDs and that sort of stuff. So I do know that it does work with that. I just didn't play around with that. I had another colleague also playing around with this at the same time. So they were able to get it to work with the middleware and the CRDs.
Okay. Awesome. Well, I think we are at time. I want to thank everybody for joining today, and for those of you who hung on for all 4 of the sessions, appreciate you taking the time to listen to us talk about Consul. As a reminder, we're going to post all these individual assets so you can watch them again, and we'll make sure that we give you the slidewares. Really want to thank all of our speakers today. Thank you all so much for taking the time. I know it's been a really busy time for us, as well for everyone who's joining. Yeah, super awesome demos, and if you have any follow-up questions, feel free to reach out to us. And then if you're interested in things like the Federation beta, you can email us on that. And 1.10 is available now, so if you want to start playing with T-Proxy, go ahead and download it. I know I've been messing around with it quite a bit. So thank you everyone for the time today, and have a great day.